The sun screams. This is not a metaphor or a poetic fancy. It is a profound scientific truth, a secret whispered across 93 million miles of empty space. We do not hear this scream with our ears, as space is a vacuum, a near-perfect silence where sound as we know it cannot travel. Instead, this celestial cry lives deep within the star itself, a constant churning roar of energy and motion. It is a low, slow, and powerful song, a vibration that resonates through the very heart of our solar system's anchor. This fundamental vibration causes the entire surface of the sun to move, to swell and shrink like a colossal, breathing lung or a bell struck by an unseen hammer. What sound does the sun truly make? The answer is not a single note, but a complex symphony, an orchestra of waves that scientists are only now learning to hear. This idea might feel strange, a blend of science fiction and cosmic poetry. The sun is not a solid object. It is a gigantic ball of superheated gas and plasma, a turbulent ocean of particles under immense pressure and heat. Within this chaotic environment, sound waves can and do exist. They are not the gentle ripples of sound in our air, but powerful pressure waves, compressions of matter that surge and rebound through the solar interior. These waves carry information from the sun's deepest, most inaccessible regions, all the way to its visible surface, offering us a way to probe a place we can never hope to visit. Listening to the sun is like performing an ultrasound on a star, revealing its hidden structures and secret rhythms. Imagine the sun not just as a source of light and heat, but as a musical instrument of unimaginable scale. Its music is born from the constant turmoil within. Deep in its core, nuclear fusion reactions release staggering amounts of energy, causing the gas to boil and churn in a process called convection. This violent motion is the source of the sun's sound, creating waves that travel outward through its layers. These waves are the sun's voice, a constant broadcast of its internal state. The silent scream of the sun is, in fact, a detailed story waiting to be deciphered by those who know how to listen. The quest to hear the sun's song is a testament to human ingenuity. It requires us to think beyond our own sensory limitations and build instruments that can perceive the universe in ways our bodies cannot. We cannot simply point a microphone at the sky and expect to hear anything. Instead, we must watch the sun with incredible precision, looking for the subtlest clues that betray the presence of these internal waves. It is a detective story on a cosmic scale, where the clues are written in the language of light. The story begins with a simple, mind-bending fact. The surface of the sun is constantly, rhythmically moving. This motion is the key that unlocks the sound hidden within, a silent roar that holds the secrets of a star. To understand how the sun can make sound, we first need to rethink what sound means. Here on Earth, sound is a mechanical wave, a vibration that needs a medium, air, water, solid ground to travel from its source to our ears. When you clap your hands, you create a sudden change in air pressure. That disturbance travels outward as a wave. The science of studying the sun's internal waves has a grand name: helioseismology. Let's break that down. Helio comes from Helios, the Greek god of the sun. Seismology is the study of earthquakes and the waves they create to understand Earth's interior. So, helioseismology is the study of sunquakes and solar vibrations to understand the sun's interior. The core idea is surprisingly simple and elegant. Just as geologists use seismic waves from earthquakes to map out the Earth's core, mantle, astronomers use the sun's sound waves to map out its internal layers, temperature, composition. The sun, in essence, rings like a gigantic bell. By analyzing the tones of that ring, we can learn what it is made of and how it works. The most prominent notes in the sun's song are known as P modes, or pressure modes. These are the sound waves we have been discussing, created by the pressure of the gas itself. Think of a drum. When you strike its surface, it vibrates in specific patterns. The sun does something similar. Its surface is constantly struck from below by turbulent convection, creating millions of overlapping vibrational patterns. The most dominant of these patterns are the famous 5-minute oscillations. Vast regions of the sun's surface gently rise and fall, with a full cycle taking about 5 minutes. This rhythm, around 3 MHz, is the sun's fundamental heartbeat. It tells us about conditions in its upper layers. These oscillations are incredibly subtle. The surface moves up and down only a few hundred meters per second, tiny on a nearly million-mile-wide star. We have established that the sun is full of sound waves, and we can detect their effects on its surface using light. But how do we actually hear them? This is where a fascinating process called sonification comes into play. Sonification is the art and science of translating data into sound. It is not a recording of the actual sound from space, because that sound is trapped inside the sun and has a frequency far too low for our ears to perceive. Instead, scientists take the numerical data collected by telescopes, the measurements of the Doppler shifts, and convert those numbers into audible tones. It is a form of translation, changing information from a visual format, graphs, charts, into an auditory one. Music, sound. The process maps aspects of the data to properties of sound. Frequency, measured in millihertz, can be sped up by hundreds of thousands until it falls into human hearing. A 5-minute oscillation becomes a low, audible hum. Higher frequency waves become higher-pitched notes. Amplitude or strength becomes volume. A powerful vibration becomes loud. A faint one becomes a quiet whisper. A silent stream of numbers from a spacecraft is transformed into a rich, complex soundscape reflecting real solar processes. This technique is more than a novelty. It's a powerful tool for discovery. The human ear is exceptionally good at detecting patterns, rhythms, and subtle changes in sound. Features missed in a complex graph can become obvious when heard as a change in pitch, a rhythmic beat, or a sudden burst of noise. The sun's 5-minute oscillations are its background music, the steady rhythm of its existence. But the sun is also a dynamic and sometimes violent place, and these events add dramatic new movements to the solar symphony. One of the most spectacular of these is the sunquake. A sunquake is exactly what it sounds like, a seismic event on the sun, analogous to an earthquake on Earth. They are often triggered by powerful solar flares, which are sudden, intense explosions of energy from the sun's surface. The force of the flare's impact can be so great that it sends ripples of waves traveling across the solar surface, much like the ripples created by throwing a stone into a pond. These waves are a much louder, more dramatic form of solar sound. Beyond the physical vibrations, the sun also sings in the radio spectrum. During solar flares and other energetic events, the sun blasts out powerful bursts of radio waves. These are not sound waves, but electromagnetic radiation, just like visible light. However, spacecraft equipped with radio antennas can detect these signals. When these radio signals are converted into the audible range, they create a weird and wonderful collection of sounds. Static crackles, descending whistles, chirps, strange beeps. These radio songs provide a real-time soundtrack to the most explosive events in the solar system, telling us about the movement of energetic particles being accelerated away from the sun at incredible speeds. Another fascinating type of wave that contributes to the sun's chorus is the Alfvén wave. This is a special kind of magnetic wave that travels along the sun's powerful magnetic field lines. The sun's magnetic field is incredibly complex and dynamic, creating vast loops and arches that extend far out into its atmosphere, the corona. Alfvén waves are vibrations that ripple along these magnetic structures, carrying immense amounts of energy from the sun's surface upward into the corona. Scientists believe these waves might be the key to solving one of the biggest mysteries in solar physics: why the corona is hundreds of times hotter than the surface below. Sonifying the data from Alfvén waves often produces a low, continuous humming or droning sound, the auditory signature of magnetic energy in motion. Together, these different types of waves and signals create a full and varied orchestra of solar sounds. The deep, resonant P modes form the bass section, providing a constant, foundational hum. The ripples from sunquakes are the crashing cymbals, marking moments of intense drama. The radio bursts are the woodwinds, with their whistles and chirps adding sharp, melodic flourishes. And the Alfvén waves are the string section, a persistent humming drone that speaks of the vast magnetic forces at play. Each of these instruments tells a different part of the sun's story. By listening to them all together, we get a much richer and more complete picture of the complex, active, and ever-changing nature of our home star. That's really something to ponder. While heliosismology has been incredibly successful at mapping the sun's outer layers, the deepest parts of the star still hold their secrets close. One of the greatest mysteries that remains is the hunt for a different kind of wave, known as G-modes. Unlike P-modes, which are driven by pressure, G-modes are driven by buoyancy, much like waves in an ocean. These waves are thought to be generated deep within the sun's radiative zone and possibly even in its core. Because they travel through the very heart of the star, they carry precious information about the conditions there, including the core's rotation speed. Finding them would be like finding the sun's deepest, most fundamental bass note. The challenge is that G-modes are incredibly elusive. By the time their vibrations reach the surface, their signal is extraordinarily weak, almost completely drowned out by the much louder noise of the P-modes and surface convection. For decades, scientists have searched for the definitive signature of G-modes, but the evidence has been fleeting and controversial. It is like trying to hear a single person whispering in the middle of a roaring stadium. Recently, however, after analyzing over 2 decades of data, some research groups believe they have finally found a faint, recurring pattern that could be the long-sought signature. If confirmed, it would be a monumental breakthrough, opening a brand new window into the solar core. Exploring the sounds of the sun is not just a journey for scientists in labs, it is a journey that everyone can be a part of. The universe is revealing its secrets, transforming cold data into something we can feel and experience. This is a new frontier of cosmic exploration, and it is happening right now. If you find this story of the screaming sun and its hidden music as fascinating as we do, we would love for you to join our community of curious minds. Subscribe to our channel so you won't miss the next chapter. Every new subscriber helps our team continue its mission to bring the wonders of the cosmos to you. Your engagement makes a real difference. When you like this video, you tell the platform these stories matter and should be shared with more people. Share with your friends or on social media and you help spark curiosity in someone new. Think of it as amplifying the signal, just as scientists amplify the sun's waves to make them audible. You can help amplify the story of science, making it louder and clearer for everyone. Every share creates a ripple, spreading the excitement of discovery across the digital world. So, what sound does the sun make? As we have seen, there is no single answer. It does not have one voice, but a whole choir. It hums with the steady 5-minute pulse of its dominant P-modes, a fundamental rhythm that has likely persisted for billions of years. It sings a complex, layered chord of millions of interfering standing waves, a harmony that shifts with its moods. It cries out with the sharp crackle and the whistle of radio bursts during its most violent moments. It trembles with the impact of sunquakes, sending ripples across its face. And it may even hold a deep, secret hum from its rapidly spinning core, a note we are still struggling to hear clearly. Each sound is a clue, a piece of a grand puzzle. This journey from light to sound is a beautiful example of how science expands our senses. We have built instruments that act as our extended eyes, seeing light and motion that are far too subtle for us to perceive directly. And now, we are translating that vision into hearing, allowing us to experience the life of a star in an entirely new and intuitive way. This act of translation requires both scientific rigor and artistic sensitivity.